Hi, this is Rahul. In this lecture, I am going to discuss about the Floyd Warshall algorithm. These algorithms find all the pair shortest paths which are present in graph G. This algorithm uses the concept of dynamic programming. If you don't know dynamic programming concept, what it means, we have a big problems. We divide the problems into sub problems, and once we computed any problems, we will store at one place, and later on if this solution is required in further computations, then we will recover back the from the same location where we had stored it. Now we will move forward. We will see how we convert this graph into the adjacent matrix. We'll see. Suppose we have these many rows and these many columns, you can see, and number of columns and rows are equal to the cardinality of vertices present in this graph. So 1 2 3 4 5 6 7 7 vertices we have, 7 rows and 7 columns we have. And if there is no directed connection between two vertices, then we are putting here infinitive. Suppose S to B there is no direct connection, so that's why we have put value here 0. S to A there is a one way is its weight is 1, so that's why its value is 1. If we verify another one, let's see A to C. A to C, is there any age? Yes, A to C there is one age, and weight of this age is 2. That's why I have written over it. In this way we can migrate this graph into adjacent matrix. We will use this matrix only to find out the shortest path between the two vertices or all pair of vertices. We'll see one by one, right? This is nothing, just the set of edges or set of vertices we have. All the pairs I have just try to make you understand how we make the pair yes to A, yes to B, yes to C in, and B to A, B to B. This is just nothing in all pairs of vertices which are present in this graph, right? We'll move to the concept. This is nothing, just adjacent matrix of this graph representation. Now we'll see the core concept of Floyd Warshall algorithm. Let's take one small path S to B. You can see I will mark it like that. You can see S to B, sorry, S to B. I have I should use another color. I will use another one. Yeah. S to B we have to find out the path. And how this Floyd Warshall algorithm works. If we go via A, you can see over here. If we go via A, then we first relax it. How we relax it? First we compute the distance S to A, then as A to B, and compare this path with already computed another part. If this path having the less weight of the shortest path as compared to this one, we update this one. Let's see how we do it. At the in the beginning, what we see, you can see the weight S to B. The S to B means what? The shortest path from S to B. If we go, we will pay price of infinity, means it is highest one. So the shortest path from S to B is cost is infinity. Now if we go via A to B from S, what will happen? We have to update the cost to reach from S to B, right? How we update the path or cost are the known distance or known cost from S to B via this matrix is what? Infinity, right? Let's write it down. This cost is infinity. I will use another color. This cost is what? S to B is infinity. I will write over here as well, right? Cost is infinity, and we want to go S to B via A, right? Then first we go S to A. S to A cost is, let's see here, S to A cost is 1. I will write over here. S to A cost is 1. Then we have reached from S to A. Now we will move to from A to B. Then A to B cost is, let's see what is 1. In this matrix, what we see, A to B cost is 1. Then I will write 1. Now you can see this 1 plus 1 is less than infinity. So if this condition is true, we do update the what? The cost to reach from S to B is by 2. This is just nothing, the same value what is present here. I hope this is clear. How many times we repeat this one? We have repeated for 1. We can repeat anywhere all the vertices which are present in this graph. For you, if any vertex which is falling between the path S to B, we update the same scenario and same thing we do for all the vertices which are present in this graph. Like we updated for A. Now we see the algorithm, how this algorithm is very simple and very just, you can very easily understand it. What we are doing, we have a path from I will take examples. You can see S to B. We want to find out the shortest path from S to B. This is source. I will write over here. This is the source and this is the destination, and this is via. As I explained here, this is the source and this is destination, this is a via. So similarly, I have written same things over here. From source to S to B, we are going to reach from S to B via U. If there is a relaxation, or if we are getting the minimum weight rather than existing weight, or if we compare the existing weight with the via U, if we can reach from S to B via U, as which is lesser than the already computed the shortest path S to B, then we update it as we are doing here. If you are able to understand this one, then you can understand. Let's compute the time complexity, which is very important one. This loop goes to cardinality of set of vertices present in graph G, and this will also go, and this will also, the number of time these instructions will be executed is weak. Why? We take a multiplication of these 3 loops, and that would be the time complex. The question is very tricky if you are asked to find out what are the paths, and if you have given the cost, if you answered the cost of any pair of vertices path, shortest path, then you may be asked what is the path. What it means, you may then you might be asked return the set of vertices which are present in the path, shortest path, I mean. So what are the changes we will make? Let's see it. Suppose we take one array, previous, and U and V. What this array means actually, how do we reach? I will write over here. You can see over P previous S to B is equal to S. What it means, we are going from S to B, the previous one, immediate previous one, which is the vertex, means the parent which explored the vertex A, which is S, you can see over. If SA doesn't equal to infinity, what it means, there exists one is, and it is not 0. What it means, this is not a this is not p and u, previous and same, we both are not, source and destination are not as same vertices. So in that case, so we update this one, right? Another one, if this any vertex which is same vertices, same source and destination, in that case we do not make any changes, because if we want to reach to vertex from itself only, the cost will be always zero. Not need to meet another via another vertex to reach itself only, right? So what are the changes we will make in this algorithms? As we have seen these algorithms, we will use this array and update it. You can see over here, I have I had updated the same things previous. We will take yes to b, and we update via this one, pub. PUV means what? You are reaching B, and from U to B, and what is the previous parent? Parent will be updated here to this one. So suppose we have an example, yes to be you are reaching, so why are you update with U if there is a direct edge. Otherwise there might be another vertex side which will be updated, which will be given to this one, right? I hope this is clear. So how do we actually print the paths which are present in any pair of shortest paths? Suppose if we have taken source U and destination V, right? We will use this array only to figure out the shortest paths between all the vertices present between U to V, right? So if we see that there is a U to V is null, right? In that case, we will return just nothing, because there is no path, or cost is infinite or something with these two vertices are not connected. So if this condition is not true, in that case what we do, we simply put the vertex in the path we will initialize with v. So what we are doing, from the last one we are inserting toward the next one. So suppose there is a vertex v. You can see we have a v vertex, and we have another, this is a previous one of v here, and previous of this one is here, previous of this one is here. Like that we are keep on updating in while loop. You can see if u and v are not same, in that case we repeat these two instructions. What this instruction is, they are doing puv means previous of uv is what, this one vertex will come here, and later on we append this vertex and we do print, right? We do actually append in this path. Later on previous of this one will becomes this one, we repeat the for same, and previous of this one we say this one. In this way we do append all the vertices from v to this side in the path and return the path. I hope this is clear. The time complexity of this algorithm is order of the path length only. I don't think so more than and the number of vertices which are present in this graph is how many? Order of v, right? The time complexity, sorry, we can write like that. Time complexity will becomes at most order of set of vertices which are present in this graph. What is the trade-off on Dijkstra and Floyd Warshall algorithms? If you have dense graph, then in that case you will use the Warshall algorithms. If you have a sparse graph, in that case you use Dijkstra algorithms. Right? Why I'm saying trade-off? Because suppose the Dijkstra algorithms find the shortest path between two vertices S to T. We can run this algorithm for all pair of vertices. So in that case also we get the same time complexity. But if you are having the dense graph, in that case you will use the Warshall algorithms. If you have a sparse graph, in that case you will use Dijkstra discussed algorithm, the time complexity of both algorithm goes to uh, order of VQ. Don't be confused. This is I'm talking about the all pair shortest path. We can modify discussed algorithm to find out the all pair shortest path. Thank you for watching this video. If you find this video is helpful for you, please like and share with your friends. That will help to make me more video for you. Thank you.